Hello? Is anybody there? Hi, Pierre. Hi, Francesco. Are you participating here already? Are you panelists already? No, not yet. So to the attendees, can you hear me? I've asked the host to promote you to panelists? Okay, so at least somebody can hear me. So I suppose that the technical chair will arrive soon, or will start doing things soon. Okay, so hello everyone. My name is Javier Esparza. I am chairing this session, and I've been given a green light from our host, from the technical chair, to start the session. So welcome. We've got 3 papers, all of them with Büchi Automata on the title, and we will proceed so that the technical chair will display the video for each of the papers, and then during the video or at the end, you can ask questions through the chat. Of course, if you are a panelist, you can also do it. Panelists are the authors of the papers. You can also ask questions just by unmuting yourself. Okay, and I would say that we start with the first paper by Havlena and Lengal, and maybe we can just start with the video directly. So the title of the paper is Reducing to the Ranks Efficient Rank-Based Büchi Automata Complementation. And then I am hoping that the technical chair will display the video. Okay, here we go.
Hello, my name is Havlena. And we would like to tell you something about our work, which is devoted to optimizations of rank-based Büchi automata complementation.
Büchi automata are a well-known formal model for describing infinite words. A Büchi automaton over some alphabet sigma consists of a finite set of states, a non-deterministic transition function, a set of initial states, and a set of accepting states. The automaton accepts some infinite word by starting in some initial state and then looping over accepting states. It is well known that Büchi automata correspond to the class of omega regular languages. Here we have an example of a Büchi automaton that accepts the word ABBA omega, and the accepting run in this automaton can, for example, be by starting in R, then over A staying in R, over B going to S, then over the next B going to T, and then staying in T over A. T is an accepting state, so this word is accepted by the automaton.
As motivation for Büchi automata and Büchi automata complementation, we mentioned three fields. The first one is the model checking of linear time properties, where the property and system both are represented by Büchi automata, and then checking whether the system meets the property is equivalent to language inclusion checking between the automata, which is equivalent to emptiness checking of the intersection of the first automaton with the complement of the second automaton. The second field is a termination analysis within the tool Ultimate Automizer, where the complementation is used to construct a difference automaton that removes traces where the termination argument has been already established. And the third field are decision procedures for logic such as S1S, ETL, QPTL, and so on. For example, for S1S, complementation is used to implement negation.
Büchi automata complementation is significantly more involved than complementation of finite automata, because Büchi automata cannot be easily determinized. The lower bound for complementation of Büchi automata is 0.76 n to the power of n, which was achieved by Yen in 2006. Over the years, many Büchi automata constructions appeared, for example, based on the Ramsey theorem, determinization-based, rank-based, and so on. In this talk, we focus on rank-based complementation, where the state-of-the-art was achieved by a series of papers by Kupferman and Vardy in 2001, Friedgut, Kupferman and Vardy in 2006, and Sheva in 2009.
The rank-based Büchi automata complementation is based on the notion of rundac in the automaton over a given word, which represents all runs on a given word in the automaton. The vertices of the rundac are pairs where the first item is a state and the second is a level in the rundac. For example, consider this automaton, then the rundac over the word B omega, you can see here. And if we want to check whether the word is accepted by the automaton or not, we can assign numbers or ranks to each node by the following ranking procedure. We start with I equals to 0, and in the first step we assign rank I to vertices with finitely many successors, and we remove them from the randoc. And in the second step, we assign the rank I plus 1 to vertices that cannot reach some accepting state, and we again remove them from the randoc. And this we increment the value of I, and we repeat it while this condition holds. Consider this in this randoc. These nodes have the rank 0 because there are only finitely many reachable successors. Then these nodes have rank 1 because they cannot reach some accepting state, and finally this single node will have rank 2. And as already proved, Kupferman and Vardy in 2001, if a word is not accepted by the automaton, then every node in the randoc has rank at most two times number of states after this ranking procedure.
In the complement, every macro state corresponds to a level in a randoc. The macro state is a quadruple SOFI, where S tracks all runs of A in the same way as subset construction of finite automata. O tracks all runs with an even rank since a breakpoint. So the O serves as a breakpoint, and in order to accept some word, we need to decrease the rank of all states and thus clear O infinitely often. F is a ranking that guesses the ranks on some level of the randoc. We focus on tight rankings, which are defined by having an odd maximum rank and cover all ranks from 1 to the maximum rank. The transition function of the complement is composed such that the S part is obtained by subset construction in the same way as in finite automata. The breakpoint, that is the O part, keeps successors of O with even ranks. So if some successor has an odd rank, it is removed from O. And F is a non-increasing tight ranking, which is consistent with the transition function. The complement contains of two parts. A part that we call weighting, which is pretty much a subset construction of the finite automaton substructure of the Büchi automata, and non-deterministic transitions into a tight part, which contains macrostates of this form and where each ranking is tight.
As an example, consider this automaton. The complemented automaton with a highlighted weighting, and the tight part is you can see here. If we consider, for example, this macrostate, and we want to get all successors over symbol B, then S prime part is a set of all successors of ST over B, which is the set ST. The restrictions for the ranking function you can see here. The only possibility is this ranking function, and the O prime part contains states with an even rank, which is T. So the only one successor is this macro state. Yeah, you can see here. Similarly, the reverse direction, if we want to go from this macro state over B, we reach only one successor, which you can see here.
The rank-based complementation approach has two main problems. The first problem is that the automata obtained are highly non-deterministically. We need to non-deterministically guess when to switch from the weighting to the tight part, and in the tight part, we need to non-deterministically guess how to decrease the ranks. This yields many different successor states when the tight part is constructed. Moreover, the tight rank bound, which is computed as twice the number of states minus 1, is often too coarse. This is often unnecessarily high, and many redundant states are generated, the states which are not actually needed in the complemented automaton. This causes state space explosion because the number of states combinatorially depends on the bound B. The optimizations that we will show later show how to reduce the non-determinism and how to keep the ranks as small as possible and thus obtain smaller automata. The optimizations are lightweight, and they are based on the notion of super tight runs. A super tight run is a run of the complemented automaton of some word which uses as small ranks as possible. In our optimizations, we guarantee that the supertight runs will be preserved, and only some runs which are not supertight might be removed in the complemented automaton.
Our first optimization, called the delay optimization, is based on an observation that more supertight runs over a given word can differ on the position of the transition from waiting part to the tight part, as you can see here, and we can keep just one of them. Therefore, we can postpone transitions to the tight part in a way that we generate transitions to the tight part only when a cycle is closed in the waiting part, which is similar to the condition in partial reduction. Consider this automaton, then the waiting part of the automaton is here, and the original shoe procedure would generate transitions to the tight part from all these macro states. However, we postpone generating transitions to the tight part from macro states P and PQ, and we generate transitions to the tight part only from the macro state PQR. Therefore, we can reduce the number of transitions to the tight part.
Our next optimization is called sucrank because it decreases the rank of some macro state based on its successors. It's based on reasoning about the waiting part of the automaton, which defines the skeleton of the tight part because it is defined the S part of the macro state. We can use the structure of the waiting part to restrict the maximum rank of some macro state, for example, by observing how big are the maximum infinitely often reachable macro states. For example, if we have from some macro state several lassos reachable, we can restrict the maximum rank of the macro state here by the sizes of the maximum infinitely often reachable macro states in some loop of the lasso. Consider the example of this automaton, which has two separate parts. In the waiting part, it looks like this, and you can see that from QS, the maximum size of an infinitely often reachable macro state is 1 because it's only R. So we can remove any macro state from the tight part where the macro state Q and S is assigned higher rank than 1. For example, here, we can see that we have two macro states when R is assigned 3 and here T is assigned 3. This is not necessary because the maximum rank necessary is only 1. So we can remove these two macro states.
The previous optimization we can refine with a minimal infinitely often reachable macro state. Consider some macro state SOF and some state Q from S. Okay, we have and S, and with some maximal infinitely often reachable macro state, and some state Q with minimal infinitely often reachable macro state. Then only these states can have higher rank than FQ. In other words, the difference between the maximal infinitely often reachable macro state from S and the minimal infinitely often reachable macro state from Q give us the number of states with a higher rank than FQ, and it allows us to reduce the maximum rank of a macro state in this way. Consider this example. The part of the complement is here, and consider this macro state. Then the minimal infinitely often reachable macro state from R is RT with a size 2. Therefore, the maximal rank of this macro state can be bounded by 3, and which is not the case for this macro state, and hence this macro state is redundant, and we can remove it from the automaton.
Our next optimization is called rank sim, and it is used to impose a relation between ranks of some states inside the macro states, and this relation is based on some notion of simulation. For each macro state in every supertight run, it holds that if two states in the macro state have an odd ranking, for example states P and R, and some simulation-based relation holds between the two states, then we can deduce that the rank of P needs to be less or equal than the rank of R. The relation is called odd rank simulation, and I will not go into technical details because it's quite involved. I will show an example where this helps. So suppose we have this automaton and we are exploring the macro states that contain the states Q1 and R1. We computed that the Q1 and R1, the relation holds in both ways. So Q1 is odd rank simulated by R1, and also R1 is odd rank simulated by Q1. So from this formula, we can deduce that the ranks of these two states need to be the same. So we can remove all macro states where the ranks are different, like here. We compute with another approximation of the odd rank simulation, which is computed as some least fixed point, starting with standard direct simulation on the automaton.
Our last optimization is called the max rank optimization, and it's inspired by reduced average Audi reconstruction by Shu. And this optimization represents several runs, including super tight runs, using a single maximal run. In a way that the ranks of the macro states in the maximal run is bigger than the ranks of the corresponding macro states in the subsumed runs. And it's used to reduce the number of non-deterministic choices, because if we generate successors over a given symbol, then we either decrease ranks of all possible states in the O set. Okay, as you can see in this example, where we decrease the ranks of states in the O set, or we continue to the maximal macro state. Okay, it's this choice. And we use this optimization in addition to the previous optimizations.
Let us say a few words about the experimental evaluation. We took the random automata over a two-symbol alphabet, which were obtained by starting with 15 states and randomly adding transitions. The benchmark is from the work of Tsai, Fogarty, Vardy, and Tsai. We reused the automata using Spot and Rabbit, and then we removed semi-deterministic, inherently weak, unambiguous, and automata with empty language, because for those we can have a more efficient complementation procedures. We were left with something over 2,000 automata for which complementation is hard. The timeout was set to 5 minutes. We implemented our approaches in a tool called Ranker, and we also have a combination of Ranker and Peterman's algorithm. Where we construct the weighting part of the automaton, we can see from the rank estimates that the complement would probably be too big, and we can do some kind of safe degradation into using a Peterman. We compared our approach with goal, where there is an implementation of Chevez construction with the reduced average out degree, Safra, Peterman, and the Fribourg construction based of subset tuples. And we compare with Spot, LTR2D star, Seminator, and Roll. So we took all the state-of-the-art tools for complementation.
In the first experiment, we compared our procedure with the best rank-based complementation procedure that we know of. It's a Shu reduced average out degree implemented in Goal. We were interested in the size of the generated state space, therefore we use no post-processing. And from the graph you can see that that we are in many cases, almost all cases, we are better. This part is the part where we are better, and know that the axes are logarithmic. And you can see that we save significant part of the state space.
In our next experiment, we were checking how small automata we can compare by various approaches. So we were using post-processing of the obtained automata by outfill from the toolset of Spot. In this experiment, we were focusing on determinization-based approaches, and we took Peterman implemented with Goal, which on average performs better than Safra, Spot, or LTR2D star in the sense of the number of states of the complement. You can see that we are still above the diagonal, so we perform better. However, in some cases, we also time out. The timeouts are on the line in the right.
We also show our comparison with Seminator on the left and with Roll on the right. Seminator is based on the semi-determinization based complementation procedure, and the Roll is using learning-based approach. From the graph, you can see that compared to Simulator 2, we are in many cases better. And on the graph on the right side, you can see that in some cases, role is performing better than we do. However, the role has much more timeouts than we have.
Let us give more details about the experiment. First, let us focus on comparison of rank-based procedures. Here you can see that our procedure was actually quite better in almost all of the cases when it finished, with the exception of 3 cases where 2 of them are due to timeout. Also, the median obtained by us is much smaller than the one obtained by Cheves's procedure. The mean is a little bit higher, but that is due to the fact that we did not time out so often. So we actually obtained sometimes quite large automata, and we think that even bigger automata would be obtained if the Cheves's procedure implemented in Go would terminate on such inputs. For the other experiment, where we were comparing the sizes of the obtained automata, you can see that Ranker has the lowest mean, with the exception of Roll. Roll is a learning-based procedure, which is actually learning the complement language. It often has obtained smaller automata. The problem is that it timeouts on almost 50% of the benchmark. Further, you can also see that the median for us is again the lowest, with the exception of Roll. In the right-hand side of the table, you can see that for all of the tools we actually won, which means we obtained a smaller automaton, then we lost, which is that we obtained a strictly larger automaton than the tool. Let us note that for our basic procedure implemented in Ranker, we have quite some timeouts, something like 15%. When we combine with the Peterman's procedure by the way of checking the size and the ranks from the waiting part of the automaton, we could put the number of timeouts quite low to something like 0.7%. Further, let us know that in something like 22%, we obtained a strictly smaller Büchi automata than any other procedure, and in 63%, we obtained at least as small BA as any other procedure.
In our work, we have proposed series of optimization reducing the state space in rank-based Büchi automata complementation. Based on our experiments, we have shown that we are competitive to the other approaches. In particular, in 22.5% of cases, we are strictly better than other tools.
In future, we wish to get more precise rank estimations according to the automata structure. We also wish to generalize our techniques to transition-based generalized Büchi automata and also to Emerson line automata. And we want to also use our techniques in language inclusion checking of Büchi automata. Thank you for your attention, and if you have any questions, please don't hesitate to contact us. Bye-bye.
Okay, so thank you very much to the authors for the nice video. So I don't see any questions in the chat. Maybe somebody still wants to use the chat for some question. In the meantime, maybe I can ask a question myself. So one of the applications that was mentioned in the paper was the verification of LTL properties. And well, there you always have the possibility for the verification of properties, but in the case of LTL, you always have the possibility to negate the property and transform then and obtain an automaton for the negation. So is your algorithm, for example, better than this algorithm, at least in certain cases? So it seems that Ondra cannot use the microphone, so maybe the technical chair can use that, can change that. They cannot unmute themselves.
Hello, can you hear us?
Yes, I can hear you.
Okay, hello. Can you please repeat the question?
Okay, the question was, in the case of verifying LTL properties, what you can do instead of complementing, which would be a way of verifying something, what you can do is negate the property and compute an automaton, right? And do you have any experience on how these two approaches to computing a complement automaton work?
Of course, if you have the LTL formula, then yeah, negate it, and that's, I think, always better, right? But sometimes you have the linear time property given in an automaton. For example, it can be, I don't know, from some other formula, like some propositional or LTL, or some let's say more expressive fragment of LTL, and then you cannot do this easily.
Right. There is a question now in the chat. So maybe I can read it out. So what do you expect in using your complementation method for language inclusion? Because of course the next paper is about language inclusion, so that fits well.
Yeah, we're slowly going in the direction. I think that so far people were mostly neglecting the rank-based procedures for language inclusion. I think that we obtained some nice improvements that would make it useful. And the thing is, in language inclusion, you can use some more subsumptions that you cannot use in the complementation when you really need to build the automaton. So we already have some ideas what we could use there. And yeah, it's open whether it will be better than the current other current procedures, like the Ramsey-based or some other ones.
Okay. Anybody else interested in asking a question? Maybe the last one. So there are several generic techniques for reducing Büchi automata. For example, delayed simulation, right? Is this something that is subsumed by your approach, or would it still bring something if you put it in addition to what you have?
I think that the automata that we started with, they were reduced as much as we could. So we put like outfield and rabbit on top of that, so that we don't get something easy to complement, and we use it as on the output also. Right. So I think these things are quite orthogonal. So yeah, we are trying. We are not focusing on some let's say things that could be dealt with by simulation. We are trying to really go into the hard parts of that can be in Büchi automata.
Okay, so then thank you very much. I think maybe we can move to the next paper.
Okay, thank you.
Thank you. Sorry. The authors are Doveri, Ganti, Parolini, and Ranzato. The title is Inclusion Testing of Büchi Automata Based on Well Quasi-Orders. And then I guess I should ask the technical chair to play the video. Thank you.
Hi, I'm Kiveli, and I'll present a framework to decide inclusion between Büchi automata. It's a joint work with Pierre Ganti, Francesco Parolini, and Francesco Ranzato. The language inclusion problem is an important problem that has been studied a lot. Different problems can reduce to it, like, for example, verifying properties on programs or even theorem proving. And here I will present our approach for solving it. So we designed a framework to decide the inclusion between two languages of infinite words. Our framework is simple. It only uses a few ingredients, and as you'll see, our pseudocode is only a few lines. It is general. First, we designed it for the case omega regular into omega regular, and then it was very easy to extend to the case omega context-free into omega regular. And finally, it is efficient. We have implemented it and tested it on different benchmarks, and it performs very well on many of them, even though our implementation is naive in the sense that it really follows our pseudocode. So we have two languages, L and K, of infinite words over a finite alphabet sigma, and we want to decide if L is included in K. Here, K will always be omega regular, and L can be omega regular or it can be omega context-free. But first, I'll explain how the framework works in the case where the two languages are omega regular, and then I will explain how we can adapt it to the case where L is omega context-free. So what we want is to find some finite subset T of L such that we can reduce the inclusion check to a finite number of membership queries in the language K, performed on elements of this finite set. So our algorithm algorithm will first compute this finite set, and this will be done by a fixed point computation over a well quasi-ordered domain. And then it will perform this membership check on the elements of the set. So now the first step we will do is to reduce the inclusion check to the ultimately periodic words of the languages. It's the infinite words of this form, so they have a period that is repeated infinitely, and such words can be represented by couples of finite words, where the first word corresponds to a prefix and the second one to a period of an ultimately periodic word. And so given a language of infinite words, we can represent the set of its ultimately periodic words by a set of couples of finite words. And so given M, U of M will always be such a representation, and I will refer to it as the ultimately periodic set of M. So now, if the two languages are omega regular, we have this fundamental result here that says that it is equivalent to check the inclusion on the ultimately periodic sets. And so we use this result and reduce the problem to those sets. And so from now on, we will only work with couples of finite words. And this, the finite set we want to find, it's going to be a set of ultimately periodic words of L. And now let's see how we are going to choose it. We are going to choose it according to two well quasi-orders. We need two of them because the first one is used to reason on the prefixes, and the second one on the periods of the ultimately periodic words. And then by taking the product of these two quasi-orders, this gives us a well quasi-order on the couples of finite words. But now, for this quasi-order to give us a correct set, correct in the sense that we can consider it to decide the inclusion, we need a property, and it's a property with respect to the language K that says that it is not possible to cross this border here, so this scenario is not possible. And we call this property the preservation with respect to K, so we say that the two quasi-orders preserve the language K, and formally it is stated like this. So U prime V prime, if it is greater than some element representing an ultimately periodic word of K, then U prime V prime must also correspond to some ultimately periodic word of K. So if we are in K and take the elements that are greater, then we remain in K, we cannot escape from it. And another way to say it is to say that, that the language K, or rather the ultimately periodic set of K, is an upward closed set for this quasi-order. So now with this preservation property, this equivalence here holds, but we are not done yet because for the quasi-orders to yield a decision procedure, we need additional condition. We need that the two quasi-orders are right monotonic. In our paper, we explain why exactly we need this condition. It has to do with the precision of the convergence check we do in our fixed point computation. But just to give an intuition, it is linked to the language L, and more precisely to the way we generate the words of L in our fixed point computation. So let's see now how we compute this finite set. First, we will give a least fixed point characterization of the ultimately periodic set of L. I will show how we do that on a very simple example. So L here is given, will always be given by some Büchi automaton, like the one here. And from it, we can derive functions for the prefixes and for the periods, like these functions here. So what they do is they take a finite set, no, they take just a set of words, and they perform concatenations on the right by some letter according to the transitions in the automaton. And then by taking the least fixed points of these functions, we obtain a least fixed point characterization of the ultimately periodic set of L. So these are the functions that we are going to iterate in our fixed point computation. But as you can see here, their fixed points are infinite sets. So we don't have convergence in a finite number of steps. But this is okay because we are going to use our quasi-orders to decide when to stop the computations. So at each iteration step, we add a finite number of new elements. And then to decide when to stop, we look at the two consecutive iterates, and we stop only if at the last iteration we have not added any new information. So this grade set here represents the information I have at iteration 1. It actually corresponds to the upward closure of the first iterate. So any element here in the gray set is greater than one of the squares that are the elements in my that I have obtained with the first iterate. And now in the second iteration, I'm adding the crosses that are outside the gray box, so they correspond to new information, so I cannot yet stop. And the same is true for the third iteration. But then at the fourth iteration, I'm adding the circles that are in my set. So its information are already had, and so I can stop. And I can take the third iterate to be the finite set I want. For those who are familiar, this convergence check we do just corresponds to verifying if the upward closures induced by two consecutive iterates are the same. So this is how we compute the finite set. So to sum up the omega regular into omega regular case, what we needed is two well quasi-orders that verify the two properties here. We also need the quasi-orders to be decidable so that we can decide the convergence check we just saw. And now for the omega context-free into omega regular case, everything stays the same, except that we need stronger monotonistic conditions. So here we need the two quasi-orders to be both right and left monotonic. And the reason why we need that is because when L is omega context-free, the way we will produce the words of L in the fixed point computation is both by right and left concatenations. Now I can show you some of our algorithms for the omega regular into omega regular case. This is our word-based algorithm, so it works by manipulating words. As you can see, it takes as input two well quasi-orders that are decidable, right monotonic, and preserve the language K. Then it first computes the finite set by two fixed point computation, one for the prefixes and one for the periods. Here, this corresponds to the convergence check. Each iterate is a set of words. And finally, the algorithm performs the membership check on the words obtained from the finite set it computed. So now, given an omega regular language K, there are different quasi-orders that we can derive from it and that verify all the right properties. But we are the most interested in quasi-orders that come from a Büchi automaton that accepts the language, like those here. So the idea is to compare the words according to the states they connect in the automaton. Here the first order is the one we use for the prefixes. and in two words compare here if they reach the same set of states starting at the initial state of the automaton. This one is the order for the periods, and for this we also need to take into account the accepting states of the automaton. So two words compare if they connect the same states, and we also need to look if we cross by some accepting state. So this is what the double arrow here represents. And just note that in the definition of this, in this definition, we always have implication here. So it's quasi-orders and not equivalence relations. So now we can instantiate the word-based algorithm with these two quasi-orders. And it is possible to translate all the operations that the word-based does on words into operations on states. And this is how we derive a purely state-based algorithm, which is this one. So it takes as input two Büchi automata, and then essentially it does the same thing as the word-based, but everything now is translated into operation on states. So here you have the two fixed point computation. This is the state counterpart of the convergence check. And in this case, the iterates for the prefixes are given by sets of states. And this is because each word is abstracted by the set of states it can reach from the initial state of the automaton. For the periods, it's a little bit more complicated because, so here we have couples of states because we look at the states that the word connect, and here we have a product because we need to also consider the accepting condition of the automaton. And finally, here is the state counterpart of the membership check the word-based does. So this is the algorithm we implemented in a tool called BAIT, and now I can show you our experimental results. So we tested our tool on different sets of benchmark. The first one comes from a theorem prover called Picken. So each instance corresponds to a theorem of type A implies B. To expose all of our results, we use survival plots or cactus plots. And the way it works is, okay, take for example the green graph, which corresponds to our tool BAIT. The point here corresponds to the 43 easiest instances for BAIT, and it needed 10 seconds to solve them. So you want to be as low as possible and as in the right as possible. Because the lower you are, the less time you need, and the more you are in the right, the more instances you are able to solve. So here BAIT solves 58 out of 60. Right behind there is goal, which solves 57. Then there is rabbit, roll, and HKC. And also notice that the scale for the time here is logarithmic. This is our second set of benchmarks, which comes from a model checker called Ultimate Atomizer. Here we have a large number of instances, 600. And as you can see, BAIT has the best performance for these benchmarks. Now we are not good everywhere. Here is our last set of benchmarks that comes from the tool Rabbit. And on these benchmarks, it's a Rabbit and roll that have the best performance. It's the red and the pink curve graphs here. On the other hand, BAIT is not able to solve all the instances. It solves 9 out of 14. But the difference of BAIT with all the other tools is that all the others use simulations, even to a great extent. For example, Rabbit has advanced notions of simulations. And what we here in the graph, here the yellow graph corresponds to BAIT with some preprocessing, where in the preprocessing we use simulations to just reduce the size of the automaton, and that's it. And as you can see, this drastically changed the performance of BAIT, because now we are able to solve all 14 instances. It is still hard. Some examples are still hard for BAIT, but at least it finishes the race. So to conclude, we have a simple and general framework. Our distinguished features are two well quasi-orders. We have two of them because we do a different treatment for the prefixes and for the periods. Now we are working to generalizing the two quasi-orders to family of right orders. We are still working on it, but so far it seems that it works even better. We are also working on extending the framework to other decidable cases, like, for example, inclusion between omega visible push-down languages. And in this case, it's also possible to find well quasi-orders to decide the inclusion. Finally, our tool is efficient. You can check it out here. It is around 2,500 lines of Java code. As I previously said, the implementation follows our pseudocode, so it's easy to understand and to follow. And I encourage you to try it. Thank you.
So thank you very much for the nice video. And I see that there is a question, that's right, in the question and answer. And then I don't know if you want to read it out and answer it yourself.
Yes, I can read it.
At the bottom is the question and answer button, or if you want, I can ask the question for Jean-Francois Rascan, who is the person who is asking it. It says, very elegant procedures. What can you say about the worst case complexity? Do you match the p-space lower bound for other regular languages? Can you keep only an anti-chain? Oh, I don't know. Maybe this was a question about the last paper at 240. No, it's a question that has been asked now. Sorry.
So we haven't analyzed the complexity of our algorithm. What I can say is that for the part where we do the fixed point computation, this should be exponential, and we can derive that by reasoning on the size of the lattices. And yes, we can keep an anti-chain of minimal elements.
Mm-hmm. Okay, so I also have a question which, but there is another question from Ondra Lengal. It seems, it is in the chat, it seems other procedures can profit from the use of simulations. Is your procedure also compatible with simulations?
So it's possible to define quasi-orders based on simulation relations. Actually, this is something that Francesco Parolini did in his master thesis. So yes, but we haven't implemented the algorithm in that case with simulation relation.
Okay. Any other questions? Then maybe I have one. So in the paper you compare with, there is a section on related work where you compare your approach with other Ramsey-based methods. So you put yourself into the block of Ramsey-based methods. But I think that's when you compare your tool with other tools, then the other tools are not necessarily Ramsey-based, right? So can you comment a little bit on that?
Yes, so maybe Pierre, if you want to answer this question.
Maybe the technical chair. Yeah, right.
Do you hear me?
Yes.
Yeah, from the other tools, they are not all Ramsey based. Like a role, for instance, it's using some learning based algorithm, I think, there. And for the others, I'm not sure. I think they are Ramsey based. So
Okay.
Goal uses complementation is based on complementation.
Goal is based on complementation, right?
Yes.
I think my question is.
Yeah, goal is based on complementation, and actually it's the Peterman's algorithm that we use there.
So that was my question: is whether is there anything to say from the now that we have implementations of both kinds? Is there anything to say about Ramsey based versus non-Ramsey based? Are there any conclusions that maybe you can make?
It's always complicated to make conclusions because, I mean, in this work we had much more benchmarks, and we could see that the picture that was depicted before our work was a bit different. So now with more benchmark, there is some other reality that emerged. If we find another set of benchmarks, then it will probably change again. So
Okay.
it's I'm very cautious here about what to say.
Right. Okay. Any other questions? You can ask through the question and answers button at the bottom of your screen or through the chat.
So maybe can I ask a question?
Sure.
So it seems from the experiments on Ultimate Automizer that you're better than the other tools. So my experience is like Ultimate Automizer, it often tries to give you as deterministic automaton as it can. So it tries to first give you finite automaton, then it gives you deterministic automaton. If it cannot get deterministic, it tries to give you semi-deterministic, and only if it cannot get a semi-deterministic automaton, it gives you some general non-deterministic automaton. So it seems that maybe your procedure is good at making use of the deterministic structure somehow. Could you say something like that?
But all the tools we compare with, including BAIT, are generic, so they don't take advantage of the semi-determinism that is in the benchmarks.
Yeah, but maybe, I don't know, so maybe your procedure maybe it helps your procedure? I don't know. It might be interesting to look into this.
Yes, I have to think of it.
So I guess
if I can add one.
Sorry, Pierre, go ahead.
Yeah, if I can add one thing. So we were in discussion with Matthias, like to have the main developer of Ultimate Automizer. So in the graphs that we have seen there, it's true that most of them are semi-deterministic. But we also asked Matthias to provide us, to turn off his optimizations to get more non-deterministic automaton. So he gave us a batch of automaton which are not semi-deterministic, and they have more non-determinism inside them, if you want. And there we were even better. Like non-determinism was better for us.
Okay, that's a good point. Okay, thank you.
Good. Any other questions? Probably not the case. So then I suggest that we move to the last paper of the session. The authors are Henning Urbat, Daniel Hausmann, Stefan Milius, and Lutz Schroeder. And the title is Nominal Büchi Automata with Name Allocation. So please, if we can play the video.
Okay, hello, I am Henning Urbat, and this talk is about joint work with Daniel Hausmann, Stefan Milius, and Lutz Schroeder on nominal Büchi automata with name allocation. So what we wanted to achieve in our paper is to get a handle on linear temporal properties of names and name allocation For instance, properties like some name is used infinitely often, or eventually, after some finitely many steps, only a single name is used. And to this end, we introduce a new automata model called Büchi Rna that, first of all, as suggested by the name, uses a Büchi acceptance condition. Moreover, it is based on an infinite alphabet to take account for the fact that the set of names is infinite. And it uses the theory of nominal sets, which gives a nice and abstract way to talk about name allocation, alpha equivalence, and related concepts. The main challenge that we have to face is that we want language inclusion to be decidable with reasonable complexity. And this is a challenge because typically for non-deterministic automata models over infinite alphabets, problems like inclusion or equivalence or universality tend to be either undecidable or decidable with very high non-elementary complexity. So what we are looking for in a sense is an automata model that on the one hand is reasonably expressive. So we would like to be able to express properties like the ones mentioned here above by our automata, and on the other hand has good algorithmic properties. So let me start by introducing the kinds of objects that our automata consume. They are called infinite bar strings. So first of all, we fix a countably infinite set of names or atoms that, depending on the context, might be interpreted as resources, for example, or variables in a program that might refer to memory cells or data values in an XML tree, for example. And we consider the following infinite alphabet A bar that essentially consists of two copies of the set of names. So first of all, every name in A is a letter in the alphabet. And moreover, for every name A in A, we have a letter called bar A that we interpret as binding the name A to the right. And an infinite bar string is just an infinite string over this infinite alphabet A bar. So for example, this is an infinite bar string that we might interpret as a process that allocates two memory cells, say, calls them A and B, and then uses A twice and B twice and A twice and B twice and repeats this infinitely often. Now, as usual in computer science, when we consider name binding, we don't really care about what the bound names are called. So we consider infinite bar strings only modulo alpha renaming or alpha equivalence. So for instance, these two bar strings down here should be considered alpha equivalent because the only difference between them is that on the left-hand side, the two bound names are called A and B, and on the right-hand side, they are called B and C, but otherwise, these are the same strings. This can be made formal using co-induction, and in fact, the formal definition of alpha equivalence, which you can find in the paper, is just a special case of a concept introduced by Kurz, Petrijan, Severi, and De Vries a few years ago. So since we want to speak about concepts like name allocation and name binding and alpha equivalence, a very convenient mathematical framework to do that is given by the theory of nominal sets in the form introduced by Gabay and Pitts in the late 1990s. So I will not give the formal definition here, but I will give you the intuition. So the idea is that a nominal set is a set of syntactic objects whose description or definition depends on names from the infinite set A of names. So to give you an example, if you take the set of all strings of length 4 over the alphabet A, then this is a typical nominal set because the elements of this set depend on names in A. Accordingly, every nominal set comes equipped with a certain structure that allows us to reason about the names that an element depends on. So for example, first of all, for every element little x in a nominal set, we have a least finite support, which is intuitively intuitively just the set of names that the element depends on. So for example, if we consider the string ABBA, then the least support is given by the set of names A and B. Secondly, there is a notion of renaming that is given by a group action of the group of finite permutations on A on the set X. And here the idea is that if pi is such a permutation and little x is an element of a nominal set, then pi times x is the element that we get by renaming the free names in X according to the permutation pi. So in our example, if we have the string ABBA and apply the permutation that swaps A and C, then we get the string CBBC. And lastly, there is in every nominal set an abstract notion of alpha equivalence. So this expression here is supposed to mean that X and Y are alpha equivalent elements of a nominal set when A is considered a bound name in X and B is considered a bound name in Y. And formally, this means that X and Y become equal when we rename A and B to some common fresh name C. So again, in our example, the strings ABBA and CBBC are alpha equivalent with respect to the names A on the left-hand side and C on the right-hand side. Note that this set A to the 4 is a very special kind of nominal set. It's what is called orbit finite, which means that it is generated by a finite number of elements. So up to application of the group action, it's actually a finite set. And this is the kind of nominal set that you want to work with in nominal automata theory, because these orbit finite sets have a very nice finite representation in terms of permutation groups. So it's time to officially define what Büchi Rna are. So this is short for regular, nominal, non-deterministic Büchi automata. And these are given by the following data. First of all, we have an orbit finite nominal set Q of states. So for instance, A to the 4 would be a typical set of states for a Büchi Rna. Then we have an equivariant transition relation that is labeled by our infinite alphabet A bar. And equivariant just means that the transitions respect the group action. And moreover, we have an initial state Q0 and an equivariant set of final states F. So if you look at this definition, this looks very much like the definition of an ordinary non-deterministic automaton, except that we interpret everything in the category of nominal sets and equivariant maps. And these Büchi Rnas are subject to two important restrictions and conditions. The first one is alpha invariance, and essentially states that transitions are stable under alpha renaming. So for instance, concretely, this means that if we have a bar A transition from P to Q, and the states Q and R are alpha equivalent with respect to the names A and B, then we also have a bar B transition from P to R. This condition is kind of intuitive, I think, because keep in mind that we want to consider infinite bar strings only up to alpha renaming. And so you would expect that the bound transitions should respect alpha renaming in some way. This is given by alpha invariance. And the second condition that we impose is finite branching, which says that for every fixed state P, there are only finitely many outgoing transitions, where in the case of bound transitions, this is again meant up to alpha equivalence. In fact, these Büchi Rnas are a variant of the concept of RNNA introduced by Schröder, Cozen, Milius, and Wissmann a few years ago. So an RNNA is essentially given by the same definition, but interpreted over finite bar strings. So the contribution of this paper is essentially an extension and generalization of the concept from this paper to infinite bar strings, as we will see in a minute. But first of all, it's maybe time to see an example. So here is an example of a Büchi Rna given by the set of states that has a single initial state Q0 and two copies of the set of names. and the transitions are given as displayed here. Note that although this automaton looks finite, it's really an infinite automaton because A and B range over all pairs of distinct names. And you can check that the two conditions of alpha invariance and finite branching are satisfied. So this is really a Büchi Rna. So what about the semantics of Büchi Rna? Well, we say that an infinite bar string is accepted by a Büchi Rna if there is a run in the automaton labeled by the bar string that visits the final state infinitely often. So this is exactly the standard acceptance condition of standard Büchi automata. However, keep in mind that we are really interested in infinite bar strings modulo alpha equivalence, and therefore we define the bar omega language accepted by the automaton A to be the set of all alpha equivalence classes of accepted bar strings. Moreover, we can associate to every Büchi Rna the so-called data omega language, which is a language over the alphabet A. And we obtain this language by just taking the bar strings in the accepted bar language and forgetting all the bars. So for instance, if we have this string in the bar language, bar A, bar B, AA, BB, and so on, then we get this string in the underlying data language that just forgets the two bars before the A and the B. So back to our example. So here's the automaton that we already saw. And one example of an accepted infinite bar string is this one here that repeats bar C, bar D, A infinitely often. And you can see that this part of the string induces a loop in the automaton that visits the final state A, 0 infinitely often, and therefore the string is accepted using the Büchi condition. Moreover, if you look at this automaton for a minute, you can see that the underlying data language is given by the set of all infinite data strings where some name occurs infinitely often. So this is exactly the property that I mentioned at the beginning of the talk, and we see that we can model this property using a Büchi Rna. So the main result of this paper and this talk is the decidability of inclusion. And this is true for both the data language and the bar language semantics. So given two Büchi RNAs A and B, we can decide whether the bar language accepted by A is included in the bar language accepted by B, and likewise for the underlying data languages. Note that these two inclusions are independent. The first one implies the second one, but not the other way around. So these are really two different decision problems, but they are both decidable. So let us briefly sketch how to prove this result. Well, there are two main challenges to overcome. The first challenge is in the fact that while we want to consider accepted bar strings only up to alpha equivalence, the accepting runs of a Büchi RNA are not necessarily closed under alpha equivalence. So if A accepts the infinite bar string V, and V is alpha equivalent to W, this does not necessarily imply that A has also an accepting run for the string W. So to see an example, here we have a Büchi RNA that accepts the bar string bar A, bar B, and so on, but it does not accept the alpha equivalent bar string bar A, bar A, bar A. So the issue here is that because in this state here we have the name A in the least support, we cannot use alpha invariance to get a bar A transition instead of this bar B transition here. So we cannot continue the computation after the first bar A when we have this input string here. And the way to solve this is the so-called name dropping modification, which essentially says you introduce a new state that behaves very much like the given state A, B, but has the name A dropped from its least support. And with this new state, we can use alpha invariance to get a bar A transition here. And therefore, we can proceed and accept this input word. So this idea can be generalized to arbitrary Büchi RNNA, and in general we have that for any Büchi RNNA, the name-dropping modification gives another Büchi RNNA that has the same bar language, but whose accepting runs are closed under alpha equivalence. So this overcomes this challenge here. The second challenge that we have to face is that a Büchi RNNA might accept bar strings with arbitrarily many names. So for instance, if we have this very simple RNNA here, this accepts every bar string that consists only of bar letters. So in particular, it accepts something like bar A, bar B, bar C, bar D, a string with infinitely many names. And this is kind of a hurdle, because if you want to decide inclusion, in the end, we should be able to break down things to finitely many names. And this is resolved by the following lemma called the Finiteness Lemma. It says that if our RNNA accepts an infinite bar string V, then it also accepts some infinite bar string W that is equivalent to V, but contains only m+1 names, where m is the maximum size of any support of any state in the automaton. So here the idea is that because m is the maximum support size, every state can carry at most m names in its support. So if we choose a set of m+1 names, then there is always one name available that we can use as a fresh one. And with this idea, we can establish this lemma. And so to prove the theorem, we use the name-dropping modification and the finiteness lemma to reduce the two language inclusion problems up here for Büchi RNNA to the classical inclusion problem for classical Büchi automata, which is known to p-space. So the idea is that using these two lemmas, we can essentially restrict our Büchi RNNAs to suitable classical Büchi automata and solve the inclusion problem there. And because the Büchi inclusion problem is in p-space, we can actually give a more refined statement of our theorem, namely that our two inclusion problems are solvable in doubly exponential time, where the extra exponential blow-up comes from the fact that the name-dropping modification that we use in the reduction introduces an exponential blow-up in the number of states. So it's doubly exponential time. Okay, so let me finish this talk by comparing our model to two other nominal automata models that have been introduced in the literature in recent years. So one model I want to mention is the one of non-deterministic orbit-finite automata, that is due to Bojancic, Klin, and Lasota. So these authors used NOFA to accept finite data words, but by using the Büchi acceptance condition, one can also use them to accept data omega languages. This model is more expressive than our Büchi RNNA, so one can accept more data languages with it. But this comes at the price of having an undecidable inclusion problem. And another model that I want to mention is the one of nominal deterministic Muller automata due to Ciancia and Sammartino. This can be seen as a version of Büchi NOFAs that has deterministic transitions, but on the other hand, a more general Muller acceptance condition instead of a Büchi acceptance condition. And so with this restriction, the inclusion problem becomes decidable. And in terms of expressivity, Büchi RNNA and nominal DMA are not comparable. So for example, the language of all bar strings or all data strings that contain some name infinitely often can be accepted by Büchi RNNA, but not by nominal DMA, and there are also separating languages in the other direction. So this concludes the talk. So to summarize, we have introduced a new automata model over infinite data and bar strings that, as we think, marks a good trade-off between expressivity and good algorithmic properties. There's some future work that I would like to briefly discuss. So first of all, if you think of temporal properties, you immediately think of temporal logic. So we would like to investigate the relationship between Büchi Rna and a suitable nominal temporal logic. Recently, in an MFCS paper, Hausmann, Milius, and Schröder have introduced a nominal logic over finite bar strings and related it to RNAs over finite words. So the obvious next step would be to extend this to infinite bar strings. Another topic we would like to investigate is, now that we know that inclusion checking is decidable, can we get a more efficient inclusion checking using techniques like anti-chains or fair simulations in some suitable nominal sense? And lastly, we would like to investigate the co-algebraic perspective on Büchi Rna. So Büchi Rna can be modeled as co-algebras of this type here in the category of nominal sets. So this brings us to the question whether we can describe the semantics of Büchi Rna using the framework of co-algebraic trace semantics, and also whether we can generalize the type functor, for example, to functors induced by a binding signature, which would allow us to treat tree automata, not just word automata. Okay, so this is the end of the talk. Thanks for listening, and in case there are any questions, I'm happy to answer them in the Q&A session.
So thank you very much for the nice video. So are there any questions? So remember, you can ask them using the question and answer channel or using the chat. Well, maybe people will think of something, and in the meantime, I can ask one. So I guess the obvious question is, what about lower bounds, right? So you show that you can solve the problem in 2x time, but and the lower bound is P space, I guess, or?
That's right, yeah, because it's the lower bound for classical automata, and this applies as well.
So do you have any conjecture in which direction it might go, or?
Well, I mean, so what I said in the talk, the doubly exponential time is not quite exact. So it's really parametric polynomial time, where the parameter is given by essentially the support sizes of the automaton. Yeah, there's still a gap. I would guess that the problem is slightly above P space in the end, but I don't have a conjecture where it exactly is.
Okay. So any other questions? I am curious about another thing, which is, so what happens, I mean, you can bind names, but what happens if you also can do garbage collecting, so to speak, whether if you can also free names?
Yeah, that's exactly, that's a very good question. So actually, when you consider our automata from this functorial perspective that I mentioned on the last slide, so this co-algebraic perspective, it is actually not difficult to alter the functor in a way that you can unbind names as well. And so we haven't looked into this, but this is also something that we plan to do. So it's a natural extension of the model. And I would conjecture that for this model, inclusion is also decidable with similar methods, but we don't know if it's actually true. It's just a conjecture right now.
Okay, so that would be a very nice result, I think.
Yeah.
Good. So, any other questions? I don't see any. Ah, yes, there is one. So in the question and answer, so maybe I can read it aloud. If I understand correctly, you are using Büchi containment also for the upper bound. But in this case, how do you get from a space bound, P space, to a time bound, 2x time?
Yeah, as I said, it was slightly lax what I said. So what I basically said, classical Büchi automata inclusion is in exponential time, and therefore our inclusion is in doubly exponential time. What is actually true is that classical inclusion is in P space, and our inclusion is in parametric P space, where the parameter is basically given by the degree of the automaton, so the sizes of the registers, basically. Yeah, so it's not exactly the best thing I said in the talk. It's slightly better what we say in the paper.
Good. Okay, so we are actually already 5 minutes over time, so I guess everybody wants to have a virtual cup of coffee. So thank you everyone, to all the speakers and to all the attendants. And then I see you all for the invited talk of Woodevin Havercourt, which starts in half an hour. Okay, thank you very much, everyone.
Thank you.
Bye-bye.